Hello everyone. My name is Tushar Khandelwal and I work in ARM Platform software team and uh, we develop basically new drivers for new IPs and do platform bring up for the reference platform what ARM makes, and we upstream platform support to different open source project and publish instructions to fetch the project and run on fast model or FPGAs to get the reference implementation working, and partners can further go and implement their own SoC or IPs based on that architecture. So I'm here to discuss about a new platform which is Corestone 700, and it's kind of an rich IoT architecture. It has a mixture of different processing elements and some new IPs for security related features. Here is the agenda, not that big, but uh, basically an introduction about the platform, system architecture, how an example system could look like, hardware security bits, interprocessor communication, an example software stack, and boot flow, and then reference implementation, what we have been doing, how this will be published, how people can access it, and future stories followed by a demo. Corestone 700, we call it as a rich IoT platform because it has mixture of different IPs and different processing elements for doing different kind of jobs. We have a mixture of elements over here, which is Cortex-A to do heavy lifting. Basically, if you are running some kind of UI on an IoT device, uh, then you can use Cortex-A. This is flexible, so people can go ahead and change it as per the architecture. Uh, you can use Cortex-M for security and for doing the IoT kind of job, like collecting data, sensor data, and moving actuators, motors, something like that. So there are security related features also, and it has a wide range of generic applications where it can be used, uh, but and it has been benefited with partnership with Microsoft, and it supports Azure Sphere client solutions. So it has helped in us in making the platform mature and taking considerations of a real product having real security requirements, where we have to use hardware for hardening the security, and it has support for trust zone technology. There is new IP which has more features, which is called firewall, and that is there basically to provide compartmentalization and sandboxing of the address space used by different processing elements. Yeah, and the subsystem will be available open source in different open source project repositories. We will publish some kind of instructions how people can download and run this system. This is how the system architecture looks like. We have a class system. As I said, to do the heavy lifting, it can run Linux, any UI rich software, and it has M class systems, which we call as external systems. It's not very clearly defined by the architecture itself, but people can use any kind of system over there which collects data or uh, like do sensor monitoring, or it could be a sensor hub, could be a camera, anything. And there we have secure Enclave, which is again an M class CPU. and it is there for providing secure services and deal with the secure boot. It is like it can act as like root of trust in the system. We have rest all things are quite common apart from firewall. Firewall is new IP, and this is there basically to provide the hardware security what I have talked about earlier, and it's there for sandboxing the address spaces of these three processing elements. And MHU is message handling unit. It is there for setting up communication between different processors, and these all entities can actually communicate to each other using these MHU channels. There are secure and non-secure channels for all kinds of communication. This is an example system, a typical use case like where you have an IoT system, you are running rich OS in normal world, a trusted OS on secure world side, handling payments and all, where you have automated payment machines. Secure Enclave is there to keep the secrets and basically provide crypto services or any kind of security related services. And external system is there to take the sensor data or do the actual job. A very good example of this could be a coffee machine, where you have UI and you select what type of coffee you want, and you can select that, and basically Secure Enclave is there to handle the payments and keys, and external system will actually dispense the coffee by running some actuators or motors. So yeah. These are the hardware security bits we have. One is firewall. There are other. These are the mains actually. Firewall is a new IP, and interrupt router is used in this architecture. Firewall is to authenticate and filter accesses to different regions of system address space in SOC. It provides compartmentalization of memory, sandboxing of address spaces used by secure enclave and host. It applies restriction policies uh, for different bus masters, and basically it has to be programmed by the most secure element in the system, which is secure enclave. So it also provides a mechanism where you can find out like who is trying to temper the firewall, or who is trying to change the configuration of, say, if someone is trying to insert some kind of malicious code to reconfigure the IP. That all can be handled by the IP itself by generating a temper interrupt, which is delivered to the most secure element in the architecture. So firewall is basically the backbone of this system. It has lots of features, and basically it can be, if you are not using some peripheral or some slave, you can turn off the firewall component for that particular save. So it's good for power management also. It supports save restore functionalities. And the other IP is interrupt router. There are lots of peripherals which are shared in this system, like between secure enclave and host system. So the address space is shared, and so you can access common peripherals from both the IPs, both the elements like secure enclave and host. So you need a mechanism where you can actually reroute these interrupts also from different IPs and different hardwares, and that's what the job of interrupt router is. It can route different interrupts to different elements, and if you're going to some low power state, you can still use the hardware by routing the interrupt to different bus master. and it also has support for temper. So temper report generation, it does that when someone tries to change the configuration of interrupt router. So it's more feature rich. It depends on your application, how much you want. Basically, firewall has lots of features, but if you don't want that, you can still use trust zone controller. This is interprocessor communication, a very basic block diagram where it shows that currently we have these three CPU versions. It can be changed as the architecture is very configurable. As I said, it's flexible. You can use any Cortex-A CPU, and Cortex-M 3 can also be replaced with V8M probably. So currently in the reference implementation what we have today, we have these three CPUs. Secure Enclave is using M0 plus. Host is using A32, that's V8 R32 CPU. External system is built upon Cortex-M3. It has its own peripherals, its own slaves like memory slaves, its own flash, its own RAM. So it's like it's it's treated as a system with least privileges in the architecture. Most of the privileges are Secure Enclave has almost all the privileges. Host has some of them. These both can communicate over MHU channels. These are MHU channels, what arrows are. Secure services can be provided by Secure Enclave. For that, we have secure channel. So as such, there is no secure channel if we don't have firewall. Firewall is actually can help you in defining access to different peripherals, and it has features for doing that, like you can access those channels only when you are in protected mode. So it has that logic, bus logic. Basically it finds out in what mode you are running, and Secure Enclave has to enforce those policies during the boot time for all the bus masters. Non-secure services could be anything, like if you want to do some kind of power management using this, if you want to check the status of something in Secure Enclave. External system basically has MHU communication to provide all the data it has to take the instructions from host CPU. Even the boot of external system is controlled by host system. Also the firmware upgrade and all that kind of story is for external system is all dependent on host, where a host actually requests Secure Enclave to authenticate all the firmware running on external system during the boot, and then basically external system boots once it is authenticated, which is controlled by host. Host has control of releasing the reset signal of external system. Yeah, and currently we are using OpenM for all this communication what we are doing, and the current implementation is in like very basic implementation. It doesn't use shared memory as of now, but going ahead we will be using shared memory. Currently all the data is passed through a 32-bit value between these IPs. Software stack, an example. So this is how we think a software stack could look like using open source components. All are open components here. Secure Enclave is running some version of software as of today. but we have plans in future to use TFM uh, and then running OpenAMP on top of it using RP message to communicate with the host and external system. External system currently is running uh, RTX. It could use Zephyr. Uh, and again, we can use OpenAMP for communication. On the host side, we have trusted firmware running on top of it. Uh, a version of Linux we are working on, it's a TinyLinux, small memory footprint XIP, running with CramFS XIP. That's very small because in such systems we are seeing that these are really memory constrained systems, and the collaboration with Microsoft actually there we have started working on a 16 by 4 system where you have 16 megabytes of flash and 4 megabytes of RAM. So that's pretty small actually for today's Linux and the file system we have. So we are working on little FS also to enable the little FS support in Linux. So we are working on the driver, writing super blocks for this, and then mounting the little FS file system as our read-write file system. It has very low memory footprint. I think we'll able to solve the memory issue what we are facing currently. And on the secure side, you can run any kind of T services. Opt is one option, but till we solve our memory issues, we can't use Opti. And moreover, it's A32, what we have currently, which is R32, and we are running TFA with SPMIN support in it. And then on application side, we could run any kind of IoT client over there, and OpenAMP is used for messaging again, and basically trusted firmware should be able to access secure MHU channel to communicate with the secure enclave, and non-secure channel can be accessed by TinyLinux from user space that is exposed in user space, and IoT client can use that channel to communicate with secure enclave for any kind of service or requesting any service, which can then handled by trusted firmware. This is an example boot flow. It's a very simple diagram actually. We have a flash image. So first what happens is secure, as soon as we apply power, secure enclave boot from its ROM, and it goes to flash and it checks for the RAM firmware image. It loads the RAM firmware, initialize some services like MHU, interrupt router configuration, firewall configuration. It does all that, and it loads it. At some point it will authenticate, but currently what it does is for AP core it is writing some jump address in the shared RAM for AP core to come out of reset, and then it releases the reset signal of AP core. And then AP core has something where it can start executing instructions. So it starts booting from its 0 address, and where you have some jump instruction, and it jumps to shared RAM, which is 4 megabytes as I said, and it goes to trusted firmware. Trusted firmware does all the rest of the things. We boot TinyLinux after. We don't use any bootloader in this system because of memory constraints. So trusted firmware boot Linux directly, and then Linux mounts the file system, and you have you can run any kinds of application over there in rich OS side. Trusted OS side, you can ask for secure services using secure mailbox. It can be initiated by Linux also, but it all comes down to what kind of service it is, and if it is a secure service, TF will take care of it. If it is a non-secure, then secure enclave will validate whatever you have given and then decides like what needs to be done. If it can handle, it will. It cannot, it will return some kind of permission denied error. Yeah, and file system, currently what we are using is ClamFS, as I said, XIP. But in future we'll be moving to LittleFS for read-write file system. Currently what we have to run is only read-only file system. So reference implementation, what we have been doing till date, it will be open source soon in future, hopefully by next connect. But it I can't assure that it will be something like what I have shown in my example as stack. It could be different, but it will definitely enable all the IPs and different hardwares in the system, and will somewhat look like this, but not exactly like this. It will provide driver reference for all the new IPs what we are introducing with this platform. Apart from firewall and interrupt router, there are more IPs which provide security related features, and yeah, mainly those, I think. Stack will have software for all three systems, demonstrating boot and communication, as I shared in previous slides. It will have boot software for secure enclave, host system and external system. We are using Yocto for all this because it helps us in, it will definitely help us in future when we start working on upgrade story of such devices. And this actually currently is helping us to create a packaged image, a single capsule image, which we can flash into our FPGA and run it. So it needs some work on different firmwares to actually parse the flash content and load the binary into the RAM. So that's it. That is all done by Secure Enclave currently. We have written some parser for Yocto images. Public instructions will be available at some point to build this stack, how to fetch this stack, build it and run on FPGA, FVP. Both will be public in near future. Future stories. So Secure Enclave, currently we have just enabled the boot software, and we at some point we will actually enable all these features of root of trust, what Secure Enclave can do with all these kind of things, and how it can handle different how it can handle boot of different systems, and it can authenticate different images once it has the crypto services available. Secure boot is another story, like how you can authenticate different images and boot the whole system, like chain of trust kind of thing. Firmware update, keeping that in mind, we have moved to Yocto, and we will build a story for firmware update also, but at this stage we are very early early development in enabling the platform and IPs. Trusted firmware M, we will be using trusted firmware M at some point. because M0 Plus is essentially a secure enclave and trusted firmware ARM. We can definitely run that on this platform to show the PSA compliance of the hardware we have. We have Cortex-A. We can run PSA compliant trusted firmware A over there. We have Cortex-M. We can run PSA compliant M firmware also. So it could be a very good platform for showing the PSA compliance of the complete platform, how this can be handled by IoT kind of devices, and how PSA actually helps in making these devices secure. We have all the hardware support for such device. And yeah, definitely secure services, which is the main job for Secure Enclave, to provide crypto services. So that's all our future story. I'll show a quick demo now. I have to show it here. Can we? Yeah. So we have a stack which is already working for all the 3 CPUs we have, and using RP message we can boot that. Using RP message we are communicating between different IPs, and I could have showed the demo if.
But we could show the demo, like, we have a demo session.
Okay.
It's all in the lab, in the PC, so you don't need any special hardware.
Just imagine a console.
Just imagine.
Yeah. Yeah, that's it from my side. Any questions?
Is the Secure Enclave Crypto Island, or is something different?
It will be. At this moment, we don't have that implementation yet in the hardware. So we are just enabling other IPs. But at some point, we'll have Crypto Island over there.
Okay. And then the other question I had, so does Linux have access to the flash somehow? Like, does Linux, like is the file system all RAM based and Linux can't access any persistent storage, or can Linux actually, through the Enclave, get to the flash somehow?
No. So it all depends on the policies what we set. How much access we want to give to Linux. Linux is treated as untrusted. So we don't. We basically apply policies like how much Linux can see the system using firewall. So Linux doesn't have to go through Secure Enclave. It can directly access. Depends what it is asking for.
You can directly access the flash?
It can, but only the region where it is allowed.
In terms of automated testing, because we're going through the trusted firmware automated testing stuff at the moment, you said it just goes to location 0, jump, and you're off booting. Presumably that happens on power on?
For Secure Enclave, trusted firmware A, you said, I think. Yeah. So that is running on Cortex-A, and that is all programmed by Secure Enclave.
Yeah, but does it power on boot?
No.
So
Secure Enclave kicks it.
Right, okay. But so when I power the board on, I've got steps I have to go through to make it boot. Okay.
Yes.
But they're programmatic and not mechanical.
No.
I don't have to press buttons. Okay, cool.
The encoding is done by, there is boot ROM in this system.
Right.
And that is one-time programmable, after power is applied. So Secure Enclave does the encoding of that area. That's around 16 bytes. And that's basically a jump address. And then TFA basically boots from shared RAM. Okay. Thank you for attending in that case.